Essentially, cylindrical coordinates are just a simple generalization of polar coordinates. For cylindrical coordinates, you're thinking about coordinates for a three-dimensional coordinate system where r is the analog of the polar coordinate r, theta is the analog of the polar coordinate theta, and you have a new quantity, z, representing the vertical position. Positive if you're above the xy plane, negative if you're below the xy plane. Z equals z. The conversion equations are essentially the polar coordinate conversion equations, and you add on a third equation, which does nothing essentially, z equals z. That's to convert from cylindrical to rectangular. To go the other way, rectangular to cylindrical, once again, it's essentially polar coordinates. R equals square root of x squared plus y squared, and that comes from the Pythagorean theorem. Tangent of theta is y over x, just like before, which does mean theta is inverse tangent of y over x if x is positive. And it's inverse tangent of theta plus pi if x is negative. So you got to look at the picture. You got to think about whether x, y, or x is positive or negative. If you draw your three-dimensional axes this way, with say x coming this way, y coming this way, and z going this way, x is positive when you're in front of the paper and negative if you're behind the paper. If you draw it this way, with positive x-axis this way, positive y-axis into the paper, positive z-axis, then x is positive to the right and negative to the left. You can draw it either way. Z is still equal to z. Nothing much to do there. Cylindrical coordinates is useful for doing triple integrals. Polar for double, cylindrical for triple. And what happens is dv equals r dr d theta dz. Trickiest part about all this stuff is understanding what's going on visually. Sometimes pictures are shown to you, sometimes they're not, and you got to figure out the picture. What's a generic kind of picture in this situation? Dare I try to draw it? Well, okay, this does apply, just like the previous example with the double integral, applied nicely when your domain was a circle, really the disk inside the circle. So cylindrical coordinates is useful when you're integrating over a cylinder. When your three-dimensional solid of integration is a solid cylinder, not just the outside of the cylinder, the can shape, but also the inside. In that case, r is a constant function of theta, whatever the radius of the cylinder is. I'm talking about this kind of shape here. Whatever the radius of the cylinder is, that's the bounds for r. If theta is going all the way around, it would go from 0 to 2 pi. And if it were truly over a cylinder, you need to figure out limits of integration for z. Maybe it's, from in general a to b. So for cylinders, it's nice. For portions of cylinders, half cylinders, where maybe theta goes from 0 to pi instead of 0 to 2 pi, or 0 to pi over 4, that would be a pi over 2. That would be a quarter cylinder. Those are examples of nice regions to use cylindrical coordinates for. In general, r could still depend on theta. R could go from g1 of theta to g2 of theta. And it also gets complicated because sometimes you think of z as going from between two functions of both r and theta. That's probably the most complicated part of it. Those kinds of situations. f1 of r theta to z equals f2 of r theta. The z coordinate in such a situation would depend on both r and theta. And trying to imagine such a region is difficult. trying to draw it is probably even worse. Are there any good examples in the book? This is supposed to be maybe a good example. Evaluate a triple integral with cylindrical coordinates. Find the mass of the solid represented by the region in space bounded by z equals 0, which is the xy plane down at the bottom of this bird cage, I guess you'd call it. And z equals that equation. Evidently, the graph of that is the top of the bird cage. The +3, yeah, takes the top of the sides are not part of the graph of this. The domain of this would be all x and y such that x squared plus y squared is less than or equal to 4. In the xy plane, that would be a disk of radius 2 centered at the origin. Plug it into that square root function, you'll get a graph that is a dome kind of shape. But to make it go up like this, you have to add 3 to it. But we do have the sides of the bird cage here described with this equation. It's a cylinder of radius 2 centered on the z-axis, really. It's like taking the circle of radius 2 centered on the origin and moving it up and down to get the cylindrical region. The density function's that, so that's the function that you integrate. The trickiest thing here, besides making sure you don't forget to do an extra factor of r in there, is figuring out the limits of integration for the inner integral. Z goes from the bottom of the bird cage, which is 0, to the top, which is this curved part up here. You got to write that as a function of r and theta. In this case, you can just write it as a function of r. Where does that come from? That comes from replacing, in this equation, x squared plus y squared with r squared. Then integrate the delta function. You also notice in this delta function, x squared plus y squared gets replaced with r squared. So you get an r squared there, but z is still in there. X squared plus y squared gets replaced with r squared, but the z stays as is for cylindrical. How do you justify it? Instead of talking about area elements, you talk about volume elements. But it's really not much harder than just generalizing polar coordinates to an extra third dimension where z equals z. It's a trivial extension to a third dimension.